Hello, and welcome to the second tutorial of the Virtual MEM Computing Machine SaaS platform. In this tutorial, we're going to demonstrate how to use our API to access and use the MEM CPU SaaS directly from your computer using code. All functionality of the Virtual MEM Computing Machine SaaS platform that was demonstrated in the first tutorial using our built-in web interface is also available to be embedded and integrated into your own applications using the MEM CPU SaaS API. The API is a RESTful design, which means it can be easily integrated into nearly any custom-developed application using any programming language you choose. For more information regarding RESTful APIs, as well as MEM Computing's API documentation, we've provided links in the description of this video for you to follow. This tutorial will feature a sample application developed in Python. The source code to this Python application will be made available to MEM Computing customers in order to help with your API integration efforts. Additional language versions of the sample code will also be available in the future. This tutorial makes use of the Community Edition of Pycharm in order to edit and run the sample Python code. Pycharm is an integrated development environment used in computer programming specifically for the Python language. In order to follow along, you'll need Python as well as Pycharm installed on your computer, in addition to all dependent Python packages indicated by the requirements.txt file, which is included with the source code. To download the required software, please follow the required software instructions in the description of this video. We suggest installing Python version 3.7.7 first, followed by downloading and installing the Community Edition of Pycharm. Lastly, you'll need to download the MEM Computing sample Python project to your PC. Again, links to download and install the required software are in the description of this video. Please contact MEM Computing customer support if you do not already have the source code. Once you've installed the appropriate software, we can run the sample Python application. In order to do so, launch Pycharm and then use the Open command to open the folder you downloaded the sample code to. Note that on a Windows PC, you may need to run Pycharm as administrator in order to load the required packages and plugins. Pycharm will load all files in the specified folder as a project and will then automatically load the required packages specified in the requirements.txt file. The project should initially open up to the README file. Double-click on the main.py file on the left. The first time you open this file, you'll be prompted to install all of the required packages as shown. Click the Install Requirements link at the top. If prompted, follow the prompts to locate and configure your Python 3.7.7 interpreter, python.exe, which you previously installed. When complete, you may be prompted to restart Pycharm for all the installed plugins to activate. Please follow the prompts accordingly. When Pycharm restarts, you may be prompted again to install the remaining dependent Python packages, so please follow the prompts. Make sure to wait for all packages to be installed. Once the packages are installed, let's hit the drop-down tab on our MEM API folder and click on the core.py file. This is the file we use to interact with our API, which contains all of the interfaces to the API that you can reuse in your own applications. Now, let's run the main file. Go ahead and right-click on the main.py file and select Run Main as shown. The sample application should now run, and a window will appear allowing us to log in with our credentials. You can also include a proxy server if needed, and then submit. If you're unsure of the login credentials to be used, please contact MEM Computing support for assistance. Here, we can see several functionalities for job management, plotting job results and visualizations, as well as for viewing jobs that have already been sent to the SaaS. So let's go ahead and create a new job. From here, we will recreate the same job we ran in the first tutorial, Club 2, which uses the Dynamic Solution Search Mode. We can choose between a CPU or GPU instance. In this case, we'll use CPU. Now here, we can enter the job name, Club 2, and open the problem file. We use the same settings we had in the first tutorial, performing just 2 iterations, a simulation time of 5, a CPU time of 60, the number of Markov chains and cores set to 36, and down below, we set our switch fraction to 0. We can then hit Submit and see that it is communicating with the SaaS and is sending the request. We can monitor the job status using the web interface or using the API. If we go back to the web interface, we can see that our job has been sent and is running. When it's finished, we can directly watch and download from the API. To do so, let's go back to the API and run the main file again. From View All Jobs, we can see how the run is going. Find that it has now finished, and select it to see all the files in the repository. We can select the files we want to download individually or just download the zip files, which will download all the meaningful files from the results of the job. So let's hit Download Zip, and now we have that in our folder, which downloads into the API repository. The sample Python application also has plotting functions to view the output from the solver. For example, the dynamic iterations plotter shows the best solution found by each Markov chain in each iteration. To view the results of the dynamic solution search job we just ran, let's select the dynamic iterations plotter and choose the history output file that we just downloaded. This plot will appear with the lowest number of unsatisfied constraints achieved plotted in blue. If all constraints are satisfied, the number will be 0 and the lowest objective function found will be plotted in orange. Recall that we ran 2 iterations, only allowing 60 seconds per iteration, so 120 seconds for the full run. We see that the best solution found during the first iteration was minus 68. That is, minus 6.8 times 10 to the 1. During the second iteration, the best solution found was minus 70, which, recall, is the global optimum. Thank you for watching this tutorial of the MEM Computing API. We hope it was informative and answered any questions you might have. For additional assistance, please contact our support team at support@memcpu.com. For more information on MEM computing, please visit our website or contact us directly at info@memcpu.com.